The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
There were a couple questions on estimations. So one person was asked for answers to estimations. I try to give you orders of magnitude and give you a sense, but if I've missed some, if you want to email me and be like, hey, I never really got this one, let me know and I can review them. And then also the other thing is I'm never going to give you a 6.7 answer because I'm rarely asking you an estimation that has that kind of answer. Like some of them do, but usually it's not even that important that you get to 6.7. It's important that you get to an order of magnitude of 10. And as long as you're there, I'm happy. And so that's why I'm not getting to the exact answer, which I know is uncomfortable and not what you're used to educationally, but it's what the estimation is there for. Another person mentioned that some people seemed like they were taking a really long time and getting sort of lost in the estimations. So I try to give you the right amount of time for the estimation so that it's reasonable, but it is something to practice getting more facile with, I guess. All right, so wind energy. So does anyone know why we have wind on the Earth? Yeah.
Because we have heat.
Yes, from?
The sun.
Yes, so it's kind of funny because wind energy is basically a funky solar energy, which I find pleasing. I don't know why, but I do. There's also some Coriolis effect stuff going on with the Earth rotating, but the indirect solar energy component is more easy to think about, and I think is the bigger component, though I'm not sure of that. So basically, you have uneven heating of the Earth. Hot air rises, causes a pressure drop. Cold air rushes in, and that movement is what we're getting in wind. So that's what's going on there. And then a lot of confusion sometimes happens. Like a lot of people see these turbines or not turbines, but mills on farms, and it's confusing. Like, what's this versus this? Is this just a junky version of this? And so the difference is, if it's a mill, it's extracting mechanical power, versus a turbine is extracting electrical power. So these mills are very high torque devices that move relatively slowly in terms of their rotation and are used to do things like pump water or grind grain. They've been around forever. They're still really common in the US and in many places for pumping water. So if you drive across the country, you'll see these everywhere. And they're still in use, and they're really nice and a whole lot cheaper to build a mill than to build a turbine because you're going from mechanical work to mechanical work. So that's very direct and much, much cheaper than doing the extra steps to get from mechanical work to electric power generation. So a wind turbine, in contrast, is electrical power. They have been around a long time too, but not basically for most of humanity, long time. And again, they're going to be moving very quickly at much lower torque. The solidity thing to think about is that when you want high torque, you want to be getting as much of the air hitting your blades as possible. So that's why there's often many, many blades or really thick blades on a windmill. Whereas a wind turbine, you want low solidity, so you want a low proportion of your blade to be in that swept area. So that's why a turbine it looks very different. So wind turbines I'm going to focus on, but I will go back to windmills a little bit at the end. You have two types, right? The horizontal and the vertical axis. The horizontal axis is what you're used to seeing around here. And what's in the news a lot, because they can go to much higher heights, and wind is much better the higher you go, basically. And so the horizontal wind axis turbines are the more common thing, at least in my knowledge, before I started doing any research into them. So there's the rotor and the motor are at the top. It has to point into the wind. The higher you go, the better. But you can imagine the higher you go adds costs and difficulty. You often try to change your blade pitch to maximize the efficiency, because depending on how fast the wind is, you want a different blade pitch. And they're now really insanely huge. So this is an insanely huge 7 megawatt turbine, which I think you can sort of see, like, is there a truck down there or anything? It's hard to get scale when it gets this big, but it's ridiculous. And some of the challenges you can imagine in building this thing is just getting all the materials to the site, because you're probably not going to build your manufacturing plant of how you build your I'm still a little off. The long blade, thank you. You know, you're not going to build your blade right on the site where you're going to want to install your turbine, probably. So then you have to get your blade there. So then you're actually limited by, like, the size of a train railroad car or a large truck or whatever. So there's all these crazy limits when you're getting up to be this enormous. So it's kind of remarkable and challenging, and this is of a scale that we're not going to be touching, of course, but it's nice to sort of see the extreme of what is out there. So this is a 7 megawatt turbine that's actually running now, I believe, and they're currently building a 10 megawatt that'll be in production in a year, or running in a year or two. So, which is a pretty big jump, 7 to 10. So, yeah, it's definitely an area that's taking off. So how, this is just classic sort of Bernoulli drawing to remind you how they're spinning in the wind, and that the motion is really dominated by the lift, not drag. One thing to think about is the need to control the spin rate. So you can imagine on days where there's not much wind, you might want to change the pitch of the blade to make sure you're maximizing the wind you're capturing. But on hurricane days, you have to make sure that your wind turbine doesn't completely just spin out of control. And so this is a really nice, relatively simple way to do it. So you can do it mechanically or electrically, or you can do it like manually. So like old wind turbines from windmills from 100 or 200 years ago, there was some poor guy whose job it was to turn the turbine into the mill into the wind, or not, depending on how fast it was. So thankfully, there's been ways to optimize that either mechanically or electrically. So this is a method where basically the weight of the tail and the turbine allows the tail to stay connected to the turbine, so that the tail, I'm getting lots of Hugh's faces, so I'll go slowly. So the turbine generally has a tail that's exactly perpendicular. So this plane and the plane of the tail are perpendicular, right? So that the tail makes sure it's always pointing into the wind, which is what you want, except when you're going too fast. Now you need the tail and the front of the turbine to not be perpendicular, but to start to hypothetically, if you're in gales, you need it to be 100, completely rotated, so that the wind is just passing by the turbine. Or if you're in a moderate wind where it's too fast for the turbine, but still usable, you want it to be off a little bit. And so the way this works is that when the wind speed gets high enough, you get some lift in either the tail or the turbine. I forget how it operates exactly. And so that allows this tail stop to be disengaged. So then the turbine rotates a little bit, which you can sort of see from this top view. These are the front views, and this is the top view. So then the turbine rotates a little bit, and then the weight balances out, and so then the top engages again, and then it maintains this angle of orientation. And then if the wind speed gets even higher, it will, again, the weights will get out of balance, things will lift, the stop will disengage. So it's a really cool system to keep your device safe. And there's a lot of them out there. And so I just wanted to show an example of what happens when you don't remember, where's my mouse, to include that or don't do it right. So watch carefully. So that was an expensive day, and they're really lucky that no one was under there. So I'll put it back so you can watch it again. Can you see? Were you saying you couldn't see? Did you make it work, or? Okay. So what?
Did the blade just fall off? Like, did it just like?
So it rotated so fast that I believe one of the blades broke off, and then once one breaks, it's totally out of balance, and the whole thing just falls apart. And it's moving at such fast speed that really crazy dynamics are going on. So yeah, so there's really solid reasons to design these right, especially when you're talking big scale. But even small scale, you can imagine in a hurricane, it's not going to be a safe thing to be near. And the small ones are often near people. Okay, so the typical components of a wind turbine, you have your rotor, you have your blades, you have a brake, because you want the turbine to be turning at a certain speed, ideally, and so you may need to provide braking before you're providing rotation out of the wind. That's another, smaller step you can take. You have a gearbox to get the speed to the right speed to power your generator. Typically on a fancier wind turbine, there's an anemometer that provides the electrical control with these yaw drives and motors to rotate the turbine into the wind or out of the wind to maximize the speed of your turbine, and then your tower. And then, so all the electricity is being generated in this part of the body, and then the power is just going down the tower. And you can imagine the challenge of when you need to do maintenance on this and you're talking about something really high up that you have to deal with it. So the smaller turbines that we'll be looking at, they're all on guide wires and on a pivot so that you can rotate them down so you don't have to climb up to do maintenance, because that requires a much sturdier tower and is a much more dangerous job. Some installation considerations that one would think would be obvious but aren't always. So this is a wind turbine that's been installed basically on a rooftop by some trees. So it's got two types of objects that are blocking the wind entirely. So this, was a many $1,000 installation that's probably providing zero electricity, because the wind may be sufficient 30 meters up, but right there is never going to be sufficient. So the good 30 meters, 30 feet. A good rule of thumb is you want your turbine to be 30 feet above any obstruction within 300 feet. And so obstructions include like houses and plants and anything else that might be in the way. So next up is vertical axis wind turbines. And you can see there's a huge range of them. And you probably haven't seen most of these in production because, again, they're not, they don't have the same level of efficiencies and benefits that horizontal axis wind turbines have, but they're a whole lot cheaper and easier to build. So for small scale solutions, they can be really ideal. There's a bunch of different names of these different types. So for example, this is called a Darius wind turbine. This is a Savonius wind turbine, which you'll be building on Friday. And this is a cool combo Savonius-Darius. The Savonius will start up automatically in wind, and the Darius won't, but the Darius gets a little bit better efficiency, so that combining sort of gets you the best of both worlds, with some drawbacks, of course, too. And so these power traffic lights in Taiwan. So there are places where these are installed effectively, and they're kind of cool, because as you can see here, You can almost build them out of anything, and you will build them out of anything on Friday. Hey, Amit, do we have enough plastic bottles, speaking of which, for Friday? So added to your homework is on Friday you need to bring in a plastic bottle, like a Gatorade bottle, a 2-liter bottle, whatever. It doesn't have to be 2 liters. It can be 1 liter or like a 20-ounce bottle. But we need plastic bottles. So if everyone brings one, we'll be in good shape. Is that doable? If you check the recycling bins walking to class, you'll find one. Cool. So some of the advantages, they're close to the ground, so you don't have any line losses comparative to the horizontal axis wind turbine. You don't need any yaw or pitch control because they're just in the wind. They're intended to be in the wind, and that works. So they work generally for lower wind speeds, which means lower heights. They're often much less noisy than wind turbines, horizontal axis wind turbines, and they can often start at lower speeds. But some of the disadvantages, they're hard to scale up. So you're never going to get a 7 megawatt vertical axis wind turbine. That's just not viable. They're generally less efficient, and they're more prone to fatigue. So they do wear out more easily because they're capturing so much more of the wind typically. But they, for our purposes, they're definitely a possibility to look at. For anything, just a reminder of the equations we're thinking about. So the force is that you're receiving is equivalent to 1/2 times rho a v squared. So v is obviously the velocity of the wind, the cross-sectional area swept, and the density of the wind. The maximum possible power extraction is dominated by the velocity cubed. So obviously velocity is going to be, your wind velocity is really going to be what you worry about when you're designing. So area is important, obviously, but the cube velocity is cubed. So the wind speed is huge. So whenever you're thinking, is this a place where is a wind turbine appropriate? The first question is, well, what's the wind speed? And then there's a coefficient of performance, which just is a reality that wind turbines are not perfect. And so there's a hypothetical limit, and if you Google the Betz limit, you can find the proof that's appealing. It's kind of cool, of almost 0.6 is your hypothetical maximum efficiency. And then a typical limit in reality is anywhere from 1/2 for a really sweet horizontal axis wind turbine to less than 1/10 for a vertical axis wind turbine that I'll show you later that's really old school, but does the job when you need it. So the other equation that you want to think about is the capacity factor. So I've seen some websites that say, like, wind is so much better than solar because wind is 24/7. Well, not really. Like, unless you're getting up way into the atmosphere, and even then there's a lot of variation. Wind is not 24/7. There's a tremendous amount of variation. And so it's generally 20 to 40% of the time is how often your turbine is generating power, which is starting to sound more like solar, actually. So that's one thing to definitely keep in mind. Okay, so a typical power curve. So at some point, at some given speed, is when the turbine starts actually turning, because up until then it can't physically turn because the wind forces aren't high enough. And then your output in terms of power is very, very low. And then you have an average wind speed generally somewhere around here, which is giving you half of the wind power, or the power that you'd like. And then you have a maximum wind speed, and then you're happy, and then at some point it gets so high that you have to shut the turbine down, or else you're in trouble. So that's just a good general way to think about what's happening over different speeds, because I'll show you later, we're going to look at data that shows you the different speeds. So these are maps from NASA that show wind speed across the entire globe. And you can see if it's very dark, it's very low wind speed, and if it's very light, it's higher wind speed. So if we could just fill this part of the ocean with wind turbines, that would be pretty sweet. But you can actually see in Nicaragua, which is right over here, you're getting pretty decent wind compared to, say, if we were working in these parts of Africa or up here in Russia or something, we wouldn't be thinking wind turbines at all. And you can see how much variation there is between January and July. And so, of course, there's a lot of seasonal variation no matter what. And you can see, like, this blue is 7 meters per second, which is getting to be useful. For a horizontal axis wind turbine, you need 5 meters per second. For vertical, you can go a little bit lower, but 5 is a good rule of thumb. And again, why we're looking at velocity over everything else is because velocity is cubed for your power equation. So, great, I've told you wind speeds. I've showed you a NASA map of the entire Earth, but that doesn't tell you much for a given location. So one way to get a really rough estimate of wind speed is this Beaufort Scale, which was developed in the 1800s. And it correlates what you can visually see and what kind of damage you're seeing to the speed. Some of the caveats on this are, number one, it's pretty rough. And especially if you're talking to people in a community saying, like, you know, tell me about wind speed and giving them examples, it's hard to remember exactly what the wind is like. Like, can you tell me what the Beaufort Scale was today walking here? I can't. Like, I don't remember. I don't really pay attention to the wind that much. If you're working with farmers, they're probably a little bit more aware of it than you and I might be, but still, it's challenging. And the other thing is that a lot of these metrics are on the ground, and we're probably talking about significantly higher than the ground, depending on what kind of turbine you're implementing. And so again, that only helps you. So if you're finding out that you're probably at 4 miles an hour, which is 2 meters per second and really low, but at the very ground level, and you're building a turbine that's 30 meters up, maybe 30 feet up, maybe you have a shot of getting enough wind. Yeah?
Is there like a uniform scale from like what the wind speed at the ground level is and then how it changes vertically?
So,
or is that a regional thing? Like, what's up?
Well, so it's both. So yes, there are some scales that can help you estimate if you know what the ground is, what it is up above, but it also is really dependent on what's around. And so I'm about to show you a tool that helps a little bit with that, but it's still very imperfect. Ideally, you'd have an anemometer and you leave it up for 5 years, and you'd have it at 10 different heights, 10 different anemometers, 10 different heights, and that would get you actual real data that you'd be psyched for. But that would be a really ridiculously slow, expensive project. And so a lot of this is just estimations and doing your best guesses. So this, I'm sorry for the web link. As you'll see, this website is like web. It's not even web 1.0. It's like web 0.5, but it has like awesome data from NASA. So you go to this website with that awful link, and then there's a bunch of different ways to get this data. And this is actually for both useful for solar and wind. So if you're worrying about solar data too, this is really useful. So if you don't know where you want to, you don't know your latitude and longitude, you can click, use the map to click. Every time you do this, you have to log in, but it's very easy to join because you just type your password twice instead of once you become a member. And then it's slow, but it looks so clunky that I was afraid you'd be turned off by it, and it has good enough data that I wanted to go through showing you it. So you have this map of the Earth. You click in the part of the Earth that you care about to center it. You click to zoom. We're in the wrong part of the world, but we're getting there. I'm gonna zoom in again. All right. And you can see, like, this is data for a region, not for a small town. So there's all sorts of limits to this data, but it's useful. And so now you can finally get your data, and now you can get crazy information. So parameters for solar cooking, for solar panels, cloud information, which can be really useful, temperature, which can be really useful, and now we're getting to wind. So you can see the variety. So you can get 50 meter and 10 meter, but because this is all satellite data or airport data, so 50 meters is pretty high for anything we're talking about, and then 10 meters for terrain similar to the airport because they're measuring at the airport because that's the place where they have anemometers. So all of this data, again, you have to take with a grain of salt, but it's good to, if you use that in conjunction with your own visual observations and talking to people, it's better than nothing, which is the alternative, or $1 million 10-year study, which isn't viable either. So we're going to just look at wind speed at 50 meters for that area of Nicaragua I just selected. And you can see a 10-year average and a minimum and maximum variation. So it's pretty helpful just to get you into the ballpark of, do I have a shot of thinking this might work? And then some of the other things that you can select for are how high you are. So Jessica, this is getting to what you were interested in, an estimate of where you are and what your ground cover is, and then it sort of extrapolates what the wind will be. So it's pretty useful and powerful. Is it 100% accurate given that it's doing really broad-based readings? Of course not, but it's the start. So it's nice. It's a nice resource to know about. So now I want to spend a little time to talk about examples of wind power in developing countries. So one is the Humdinger wing belt, which is totally different from what you're used to seeing, and was developed by a student who actually took one of the first D-Lab classes when it was the Haiti class. And we have a wind belt here, but I couldn't find it, so maybe during break I'll be able to dig it up, or if not, maybe we can dig it up by Friday and show it in lab on Friday. So the way the wind belt works is that instead of a rotation, it just uses the vibration of the belt, very similar to, I don't know if you guys can remember the name of the bridge that collapsed. Yeah, does everyone know the Tacoma Narrows Bridge? Yeah, so well, Google it because you can see videos and it's awesome if you haven't. So yeah, it is totally scary, especially because I have a friend who did some research into it, and so this bridge, there's a super long bridge, and it just had natural frequencies at the same rate as the wind was often blowing, and so the bridge would just go up and down crazily, and eventually one day it got so bad that it completely broke apart. And the crazy thing is that people used to hang out on the bridge on the really windy days because it was so fun. It's like a roller coaster. And so it's extra scary thinking about that. So anyway, but this was the sort of the inspiration for the Humdinger, which just has a really tightly pulled belt in the middle of a support structure, so that and you put this wind, so the wind is going perpendicular to the board, and so that hits the natural frequencies of the belt and causes it to vibrate. And then you just have some magnets next to a coil on the corner that allow you to generate electricity. So for certain applications, this can be a really low cost way to provide electricity, and this is a pretty relatively fancy way of building it, but you can imagine, and they have, building it out of like a PVC pipe, which you can get anywhere, and building it really simply. And because there's very few moving parts and nothing rotating, it's much easier to build than even a vertical axis wind turbine. And so it's a really neat application, and hypothetically you could imagine building it into structures like railings on buildings and stuff, in order to power different things. So this is one example, and we do have at least a couple at D-Lab, so we'll make sure to show you them later today or tomorrow. Another example is there's sort of the classic wind turbine in developing countries was designed by Hugh Pickett, and these are pictures of work being done at Blue Energy, which is in Blue Fields in Nicaragua, and we worked with them last year. And they build all these turbines. So you can see there's the support wires, and that you can rotate the turbine down so that you can do maintenance on it, which is a really nice feature. So that's one sort of classic design that's pretty common in developing countries. And then a lot of people have heard of William Kamkwamba. Oh, there's the wind belt. So let me go back to that. So I'll pass this around, and the belt is not exactly taut at the moment, but you can see just the belt, the magnet on the belt that goes against the coil, and that's really all there is to it, and then a little bit of circuitry in order to generate power, which is a really simple way to do things.
So what's the idea? The wind goes through the tape there.
Yeah. And the tape vibrates because it hits natural frequencies, and the vibration allows you to generate electricity. This movement is all you need. Thanks. So William Kamkwamba was this guy. Where did he live? Did I write it down? In Malawi. And he just got really interested in how he could get electricity at his house, and went to the library and read a bunch of books and got inspired and built his own wind turbine, which doesn't look like your traditional wind turbine. There are a few design improvements that could be made, especially with better resources, but worked well enough for him to power a radio at his house and charge cell phones, which got people really excited, so that then they would start paying him so he could start building more and more turbines. So it's a really cool story, and now he's at Dartmouth in school, which he never could have done had he not built this turbine. So he's a cool guy. We may be able to get him to come down to talk to our class this year. We'll see. I'm trying. But his advisor at Dartmouth is very reluctant to let him travel. I'm sorry? Yeah. So, but because he didn't grow up here, like, he's getting very parented at a different level than you guys are. By the professor at Dartmouth. So anyway, so just a cool example of something very low tech that worked really well and made a remarkable change for this guy and also his village. And then working all the way down to the really simplest wind turbine. So this is I don't know if you say it as Panemone or Panemone, but one of those wind turbine, which is incredibly old technology. This is the 10,000 BC technology that we're talking about, and it's just sails that rotate. The sails actually, each one rotates 180 degrees, so they're always moving in the wind. And this is not a turbine, this is a mill. So the act of it spinning pulls this rope pump. Maybe if I turn off the light so it'll be easier to see. So there's a rope pump here, and the way a rope pump works is incredibly simple. You just have a rope inside a tube that goes down into the water table, so that you're filling, you're getting water through holes in the tube, and then you either have knots in the rope, or if you can find them, rubber washers, like every foot along the tube. And this is obviously not to scale in any way. And so the water gets trapped between the washers, and you pull up the water that way. And so this is really simple. Again, we're talking about ridiculously low efficiencies, but if you need to irrigate, this is a way to do it that just uses the wind, that works really well. So, and this was built for $40, so, which is ridiculously inexpensive compared to even like a Hugh Pickett wind turbine, which is, you know, in the thousands of dollars. So there are opportunities for a whole range of possibilities. And then, yeah, there's just so many different types out there. So if you look into it, wind is one of the areas where people get really excited and like to build their own stuff. And so you can see a huge variety of designs in the world. So that's wind in a very fast nutshell. Are there any questions about that? Okay, so next is MicroHydro. And MicroHydro is kind of funny because it's harder to find really good examples of installations in the developing world because they tend to be just built but not well documented is what I'm finding. So, I'm going to talk more about how you would determine if a MicroHydro installation would be appropriate, and I don't have as many good examples of installations that are successful, but they're certainly out there. So hydropower is just using the gravitational flow of water to generate power, considering both the two terms I'm going to use are head and flow rate. So head is the distance that the water falls, and flow rate is how quickly the water is moving. And so hydropower can be at 2 megawatts and much beyond, and can be a sizable, it is a sizable impact on our nation's electricity supply, for example, all the way down to a 200-watt turbine or smaller. So I'm saying microhydro for this lecture. Probably some of the stuff I'm talking about is actually pico or mini ranging. And everyone defines these differently, so if you look up what picohydro is, you'll see 10 different definitions. So it's not critical that you're getting exactly, and you can even see there's between pico and micro, there's something, right? So according to this definition. Yeah, so, and this is, with water power, it's the same as wind in terms of there's mills and there's turbines. So you can think of the old grist mills and other things that you can see in parts of New England still. They're low velocity, high torque, delivering mechanical power directly, as opposed to a turbine, which is much higher velocity, much lower torque, to allow you to generate electricity. So those are the two extremes. Yeah. In terms of hydropower, there's two methods. So one is called run of the river, and that means that you're just taking a chunk of the river and siphoning it off into a tube that goes directly into your turbine. And the other option is a dam. So the benefits of this are that it's relatively simple. You can build it locally, compared to a dam is much harder to build generally. It's comparatively much lower environmental impact than a dam. They're relatively affordable, but when you have a drought, you don't have any storage like you have with a dam, so that's the drawback. And the dam is, the reverse, that you can accumulate your rainfall, which is great, but it's relatively expensive, and there's a greater environmental impact on the negative, because damming up water affects the local environment, from the fish to just what the fields look like, et cetera, et cetera. I'm sure you've heard of dams in China or similar that have destroyed many entire communities for building dams on a very, very large scale. And then, and there's more maintenance associated with the dam too in terms of silt accumulation. It's challenging. So we're just going to talk about the run-of-the-river model. So the components that you have is something called a weir that diverts a chunk of the water into your tube. You generally have a settling basin so that any debris settles out. because you don't want it going into your turbine because you'll destroy your turbine. A 4-bay, which is a small holding tank, so you're getting reserve capacity that way, but that's talking about like variation on the order of seconds or minutes, not days or months. Penstock, which is a closed pipe flowing downhill that feeds directly into your turbine that then generates your electricity, and then the water is returned back to the river. There's a lot of different turbine types. So one of the most efficient, if not the most efficient, is called a Pelton Wheel. And you can see it's got a relatively complex geometry. And so relatively expensive and challenging to build. But if you do, it's very efficient. It works well for a high head, low flow situation. So again, head is how far the water is dropping. Francis wheels, which work better for lower head, higher flow, which has a spiral casing where the water comes in and spins this turbine and then comes out. Cross flow, where the water flows over this cylinder, which has a bunch of blades on it, and that's what spins the shaft to generate electricity. A propeller, which literally uses a ship's propeller, and instead of the ship's propeller being powered in order to move the boat, it's using it in the exact opposite way. And you can see that these, you need different types of turbines for different flow and head situations. And then one example is just literally putting something in the river, skipping all that extra stuff of filtering, of siphoning off the water and just putting something on top of the water, which seems really simple and great until you think about like all the challenges in terms of flooding and debris in the water and et cetera, et cetera. This is a device that is really prone to failure, but it works in areas where that's your only option, or it can work. Yeah. So some of the considerations you need for MicroHydro, one is that the minimum head and flow you need is 3 feet of head and 20 gallons per minute of flow. So that would be the minimum head you need. And if you have more head, either bonus, you get more power, or you can therefore have reduced flow, because the power equation here is, again, a coefficient of efficiency times the water density and gravity times the height, which is your head, and Q, which is your flow rate. So you can see that HQ you can keep constant. If you increase your head, you can lower your velocity and keep your power constant. One nice just rule of thumb is if you stick with SI units, rho G is about 10. So you can just plug that in rather than having to remember the density of water and gravity, though in SI units that's relatively easy. But if 10 is a nice way to just remember it. And then efficiency is somewhere generally between 40 and 70%. One other thing to think about is just when you have your penstock, so that's the water going through the pipe to get from the top of the river down to your generator. If your pipe diameter is too small, you're going to have frictional losses in the pipe that dominate and slow your water down so much that it's problematic. So that's another thing just to remember, because it's tempting to use small diameter pipe for a variety of reasons, but that's dangerous. So how do you figure out if a river is appropriate for using MicroHydro? So the two things you need to know, again, are flow and head. So the simplest method I can find for measuring flow is called a float method. And you can imagine actually doing this in a river would be challenging, so it's not trivial, but it is possible. So you mark about 100 feet along a length that's ideally straight with uniform length and depth, or width and depth, which is comical to find in a river, right? Like I've never found a river that has 100 feet of uniform width and depth, but you do your best. Then you calculate your cross-sectional area A. People usually model it as a semicircle or a trapezoid or even just a rectangle. Calculate that cross-sectional area. You place a marker at the start and end of your 100 feet, and then you put floats in the river at the center of the stream and time them to find out how long it takes for them to get from one end to the other. If you want to get complicated, you can put them all along a bunch of different points at different levels to worry about friction losses, but you don't actually have to do that to get a ballpark measurement. You can just do it in the center. And good floats, it could be a tennis ball, it could be an apple or something like that, whatever you can find that floats. And then you do have to use a conversion factor because your water's flowing faster at the top of the water than in the river than in the center because of the friction associated with the base of the river. And so you have to, you can use a coefficient just to correct, and then you get your flow rate. Yay! So that was a lot of work, and all you have is a flow rate for one day. And water varies, like flow rate varies tremendously during the season. So again, you can do your 10-year study, or you can just get some data on annual precipitation and when is the rainy season, the dry season, and do your best to estimate. But yeah, so that's how you'd get your flow rate. And then in terms of head, the simplest method that I found that's used is you take a yardstick or a stick of known length, it doesn't need to be a yardstick, and you put on it just a tube that's clear that has the ends capped, that's half full of water, and that's a really cheap level, basically. Or you can get a real level if you have a real level. But if you don't have a real level, you can just use a cheap level. And then you, hopefully with two people, you put the stick at the bottom or the top and then just keep moving it over and over again until you measure your head, which is a pain, but people do it and it works. And actual surveying equipment is really expensive, and so you're unlikely to have that in the field. So if a community partner asks about this, you have a method to measure that's plausible. Yeah?
Sorry, I thought the head was the drop into water.
Right.
So you're putting this in the river, like perpendicular
No,
to the water flowing through this one.
so for the flow measurement, you're putting your floats in the water and watching how long it takes to get from one end to the other. And that'll give you a measure of flow. And then your river ideally is, let me get a picture instead of trying to draw a bad picture. So your river is hypothetically going down the mountain here and sort of doing a curve. And so you're saying, okay, well, I'm gonna put my weir and everything up here, and I'm gonna put my location where I'm gonna actually generate the power down here. So I need to calculate the height from right here to get my head height. So now I need to, very painfully go up the mountain in order to figure out exactly how high this distance is. Does that clear it up? Okay. Okay. So that wraps up MicroHydro. Are there any questions in addition? Okay. So trip. I want to start talking about the trip and spend actually the rest of the time talking about it. So yeah. So let's do that. So one change is that one group of students is going to go to El Salvador now instead of Nicaragua. And the reason for that is Amy Smith just came back from a trip to El Salvador where she found a community partner that's really interested in us, and we think they're doing great work and are a solid connection. And So we decided to see if we could add Nicaragua or El Salvador, and we're able to in about 2 hours, which is remarkably fast compared to like the months it takes to develop relationships with other community partners. So hopefully that's a good sign. And they're really interested in charcoal, which is something you'll be trained in next week. So it just seemed like a good fit. So and you already know about this group, so I'll talk to you offline if you want about it. But yeah, so we're excited to be working with them. So one group of students is going to be going to El Salvador, and then 2 teams will be going to Nicaragua. And El Salvador doesn't border Nicaragua, but it's pretty close. So we're not that spread out yet. We're not approaching D-Lab development quite yet. So the teams are as follows. So also Phoenix will be going to, Bus, Rosser, and Brianna will be going to also Phoenix, and Carter, you'll be working with them for the start of the term. Just, I don't know if I've mentioned this, the teams that you go with to and the projects you work on for the spring break trip may or may not be what you end up working on afterwards. So what happens is the week after you get back from spring break, we sort of figure out what projects are going to happen. You tell me what you prefer to work on. And some students are really psyched to stay on the project that you went on spring break, and naturally I'm going to try to make it possible for you to stay on the project you're really psyched about, and especially if you're knowledgeable about it because you just went on a spring break trip, great. But if for whatever reason you're like, you know what, I can't stand also Phoenix, I don't want to work with them or any of their projects ever again, I'm not going to force you, hopefully not going to have to force you to stay on that. So there may be a little shuffling. So especially the people who aren't traveling, there's variation. And I'm pretty sure Eric has dropped the class, but if he hasn't, he would be on this group. So the projects that you're going to be working on, one is last year the students worked on the OJ bag sealer. And so one thing is delivering that bag sealer, which ideally means reading the final report from last year and learning how it works so you can show it to also Phoenix staff when you get there. And that's sort of like the side servicey project as opposed to the investigative parts of the work. And then the 1, 2, and 3 are the projects that you're going to be investigating. So one is the biodigester, which is, they have biodigesters and they want to be able to mix internally so that the slough provides better digestion. And they're looking at either hand or bicycle power. And they have both concrete and plastic biodigesters. The second is a feed chopper mechanism using bicycle power, and I can show you video of the feed chopper. And third is a washing machine. D-Lab actually has done a lot of work on washing machines, and so this is one area where you can learn about the existing washing machines designs and then potentially bring them down and even build one while you're there is a possibility. And at the end of going through all this, I'm going to talk about what you need to do with this information in the next few weeks, and then you'll have time to work with your teams, talk to me a little bit. Your mentor will show up at 2 to work with you a little bit on all of this. The second group of Juan, Jessica, Elizabeth, Vivian, Sid, and Kurt is going to Grupo Phoenix. Amelia Servi is your trip leader. She took this class last year and did a summer fellowship at Grupo Phoenix, and so she knows them pretty well. And she's a grad student now. And so the projects are, number 1, they're really interested in charcoal, both the stove and a stove project that was worked on last year and making charcoal generally, so working with them on charcoal. 2, solar cell phone chargers to develop more affordable version for production. They currently are working on developing a cell phone charger. I can show you the battery charger they have, and it's pretty rudimentary, and partly that's a function of their poverty and availability of materials, but there is opportunity to improve it, and they would like to have a really good solar cell phone charger. And then 3, they have a solar cooker that's really expensive. I'll talk about it next week some. And there's a lot of opportunity for improvement there to make it more affordable to produce and more aesthetically pleasing and more functional too. We have some data on there. And then the third group in El Salvador is called ASOPROSAR. And so Benzi, Missy, and Yulia will be going there, and Adrian and Benji, you'll be on that team too. And so the projects, so they're interested in charcoal training, and that again, so that would be sort of the service part. Better ventilation for smoke in the home is one area of interest, we believe. Secondly, is we think charcoal stoves will be relevant in El Salvador based on what I remember of my trip there. I'm pretty sure they cook with adobe stoves just like they do in Nicaragua, so it'll be relevant to work on the stove project there. And then potentially better lighting opportunities too. And a lot of these are sort of have a bit of an architectural bent, which we haven't focused on much in this class, but Yulia is a grad student in architecture, so she's going to help with that aspect of things. Guess what? So yeah, so we're excited about that project, and thanks for the people who are rolling with just being sent to a new country with very little notice. So what do you have to do with all this? So right now, and by right now I mean in the next 2 hours, talk to me and do some brainstorming of ideas. And your deliverable for this step is 2 annotated pictures from each team member. And so there's a lot of different deadlines for all these different things. I'm just trying to help you get through the next couple of weeks in a way that you actually get output and don't save it all to the last night, which will lead to really weak both packing and help for your community partner. So this is all hopefully in preparation so that you can maximize the value to you and your community partner for the spring break trip. And for the people who aren't traveling, you're helping make sure they're maximizing their work, and it's also getting you prepared for doing the project work after the spring break. So I don't think this is busy work for you in any way. So that's one, is doing a brainstorming effort, and I'm going to talk a little bit about brainstorming in a minute so you have some guidelines there. Yeah?
Pictures, you mean find examples of existing technology or like do sketches?
No, just sketches. So yeah, so basically I'll show you this in a minute, but when you do a brainstorm, like if I was brainstorming wind turbines, I might do a picture that looks like that. You know, like takes me 10 seconds to draw tops. And for the pictures, and that would be really appropriate in a brainstorming session. For the pictures you turn in, I'd want it to be a little more refined so that everything is drawn a little bit more carefully. There's a few more elements that actually make this a real device rather than just something disembodied in air, whatever's appropriate. Not many, if any of you, are artists, right, or technical graphic designers, and so I'm not looking for an amazing sketch that was done by a graphic designer or artist. I'm not one either, but if you just draw relatively slowly and carefully, you know, and maybe do a couple tries, you should be able to get a drawing that looks decent enough that it's understandable, which is all I'm really looking for. So then the second thing is a literature search on the topic, which you may have time for as well, but I want you to do a brainstorm initially just to sort of get creative before you know what's out there necessarily. So that's why we're doing the brainstorming first, but then a second set, which you may have time to do some today if you brought laptops or what have you, is to get some information on what's out there. So that you're more informed about whatever you need to be, whatever your project is. So what I think would be a good deliverable for this is an annotated bibliography, and there's guidelines right there on how to write an annotated bibliography. The guidelines for annotated bibliographies are generally on the liberal arts side of things, and so they talk about summarizing what was the content, reflecting on whether it was useful, and assessing the quality of the source, and all those things are good things, but basically I want you to focus on summarizing what was there and reflecting on how it's relevant to your project for each annotation, and assessing the quality of the source. If it's a crappy source, just don't include it in the bibliography, and if it's a great source, include it. And if there is something to assess that you want to note, don't hesitate to, but otherwise you don't really have to spend time assessing the source in a written form. So third is developing project specifications, and 2009 does a really nice job of defining what a project specification is. So I've provided links to their lecture and examples. And so you're going to provide project specifications for each project using the 2009 format. So that would mean an attribute, a metric, a unit, and a value, and you'll see the definitions there. The value is an actual number, like it needs like a 3 or a 7, and a lot of those numbers you probably won't be able to fill in until after your trip, and that's fine. But what I would like you to do is come up with the best guess, even if it's a range of a couple of orders of magnitude. Come up with the best guess so that when you talk to your community partner, who often don't have a lot of comfort with numbers and may give you really wacky numbers, if they're giving you numbers that are completely different from what you're expecting, that's a really good indicator to you that you need to keep asking questions so that either you learn that your assumptions are totally off, which is a really important thing to learn, or that your community partner isn't really understanding the question or doesn't have the educational background to be able to give you a useful number, and you have to work in a few different guises to actually get to that number. And we'll talk about that on the trip prep week of how you actually do that process of getting that information. And then the next aspects are doing a second brainstorm, and it's up to you as a team if you want to do this in 2 stages. So sometimes people like to brainstorm on their own for a bit and then come together and bring those ideas to a brainstorm and also build on more in a group brainstorm session. Some people prefer just to do a group brainstorming session, so it's up to you. But the second brainstorm should at least have a group component. And for those, it's just 2 annotated pictures for each project. And so it's fewer pictures because it's not per team member. And so you guys can just figure out how you want to split those up. Another thing is the big questions you have that you want to make sure you get answered, so that you have those in mind, so that you make sure by the end of the trip you've gotten answers to those questions. And all of these questions are related to figuring out, can you actually work on this project? Is this a good project? And if you are going to work on it, what is the appropriate deliverable? That's the type of questions. A materials list for the trip. So you may well need some materials if you're going to do a charcoal demonstration, if you're going to try to build a washing machine, if you have a great idea for a project and you want to try to actually implement either a prototype or something in the field, your community partner needs to know so that they can provide the materials, and or we need to get them here so that we can bring them down. And so I put that you don't need this until the 16th, which is right before the trip. And that's only if, like, that's the last desperate time. If you can define them sooner, that's better, so that your community partner has time to get them, and or we have time to get them if you need help. Oh, no, that was questions. Materials is earlier. Okay, good. That makes more sense. And then finally, on the 16th, you're going to do about a 15-minute presentation on your literature search findings, your project specifications, the annotated pictures, the key questions, and your key expected activities, just so that you're well prepared for the trip. So that's basically the assignments, apart from a little bit of reading for the next few weeks, which again violates the syllabus, but hopefully will work out. So, or be okay with you guys. But I didn't want to add problem sets on top of this because this is a lot of work. Are there any questions about all of this? I have it printed out so that when you're working on it today, you have something to refer to. Yeah.
Did you get the dates for the flights yet?
Yeah. So most people are flying on, people going to Nicaragua are flying on Sunday and getting back on the following Sunday. What about El Salvador? Juan and Jessica have personal commitments, so they're flying back on Friday. And do you know what El Salvador is doing yet, Amit? Okay, so El Salvador may be traveling a day earlier. So.
Whatever the
Maybe.
days are.
I think so. Yeah, the 18th is the Friday, so the Sunday would be the 20th. And we'll send out your actual itinerary soon. Some of the tickets are booked, others are just reserved, and we'll be booking them today. So there's a couple of reading assignments that'll be up on Stellar shortly. This is just a somewhat different perspective from the Paul Polak reading you did. And then this is directions on charcoal making. So both are quite short, so I know it might be seeming like a lot, but these are very manageable to get done. So now I just want to go over how to do brainstorming, and then we can take a break, and then you can get into your project groups and do brainstorming and start talking about the trip. And then at 2, your mentors will show up, unless your mentor is on meet, he's already here, or trip leader. So you can get support from them as well and get to know them. So effective and fun brainstorming, you require a clear problem statement. So for this case, it's whatever the project idea is for your community partner project. After you get back from spring break, you have about 4 weeks of building, and you have about a $500 budget. So while you'll see, I'm going to encourage you to have really wild ideas. And so if you come up with an idea that completely violates the 4 weeks of building and the 500 budgets, still throw it out there. It's nice to have in your mind a general sense of these sorts of things, so that you're not only brainstorming things that are in the like 7 megawatt wind turbine category, if you're thinking about wind power. So for fun and effective brainstorming, you're trying to generate as many ideas as you can in 15 minutes. So 15 minutes is a good length of time. Sometimes you need a little more, a little less, but around that time for any particular project statement. And then you can say take a break, take a stretch, and then come back and work on the next problem statement. You want your sketch to really be a picture with a few words. So a lot of people, if they're brainstorming weapons of war, and you have your 8.5 piece of paper, might draw this. And I would say that this picture is a lot more evocative of what your idea is than using the words big and just a tiny drawing. And those of us who are not so good at drawing, and I'm one of them, are tempted to draw really small because you don't want to show in really big format just how bad your drawing is. But even being a weak drawer, you can still get your idea across pretty well. This is like a 3-minute sketch for an artist. So none of your brainstorm ideas are going to look this crafted. This might be the actual annotated sketch that you turn in, that you actually refine and spend some time on. So, the 10-second version is going to be a guy, and you have a guy, and he's shooting stuff, and here's the person who's unhappy, getting shot at, and then here's the wheel that's moving your wall of doom, right? So this is a really fast version of that sketch, and so that's what I'm looking for, not that. But I just wanted to emphasize, most people start out doing this, and you really want to force yourself to do that with maybe the description at the top or the bottom, but the picture should dominate, not the words. Yeah.
So I'm still a little confused as to how the 3 projects that you listed on each slide relate to the brainstorming and the sketches.
Okay, yeah. So the 3 projects. So if one of your projects was the feed chopper, right now you know nothing about that project, right? So you may not be able to brainstorm that at all until you come talk to me, which is part of what you need to do in the next hour and a half. Is come talk to me, so I can give each team a little bit more detail about their 3 projects. But one of them might be something you can brainstorm on initially if there's a queue to wait for me. But either way, once you know a little bit about the feed chopper, then that'll be one of your brainstorming assignments. Is the project, the community partner needs this mechanization of the feed chopper, and let's brainstorm ways to mechanize that feed chopper. and just put out as many ideas as you can in 15 minutes. And a good goal is to be generating like at least 3 ideas per minute, which doesn't sound like that many, but it's pretty challenging. But that is sort of something to keep in your mind, is I should be generating 3 ideas per minute. And so if I'm not, I need to get crazier, probably, and less inhibited in order to successfully do it. And so once you draw this beautiful picture with your group, what you do is everyone's hopefully drawing, and you just say, hey guys, my idea is an advancing wall of doom. And then you grab a piece of tape, and we're going to use the 3 fume hoods as our boards. So each group will be around a fume hood. And so just tape your idea up on the wall, and then get back on drawing. And if, Kurt, you had said this advancing wall of doom, and I loved that idea, I can say, yeah, it's going to be an advancing wall of doom, but instead of being wheel-powered, it's going to be on a big wheel powered, it's going to be on a bunch of little wheels. And so in other circles, that might be considered theft, right? And you'd be really mad at me for stealing your idea. But in brainstorming, that's really encouraged, is to, quote, steal people's ideas. So have no worry about that. You guys can work out your patent rights if you become millionaires over your advancing wall of doom later. So what are the rules of the game? So one is deferred judgment. So when I propose that I want to make a wind turbine that's just going to float in the air magically with helium balloons, and you see a few flaws in that idea, you just have to bite your tongue, right? And the one way you can manage that is by saying, okay, I'm going to still take your, I'm going to build on your idea, and instead of helium balloons, we're going to use a post that's attached to the ground. But deferred judgment, even of your own ideas and of anyone else's. If you're showing your idea, no saying, this is really stupid, but here it is. Just say what it is. Hopefully everyone is coming up with some really terrible ideas as well as really, really good ones. And some of those really terrible ones have a kernel of awesomeness in them. And so that's why it's worth it to get them out. One at a time. So if everyone is talking at once, it's ineffective. So post them up one at a time. And you shouldn't draw like 3 ideas on 1 piece of paper. You should have each piece of paper for each idea. As I mentioned, so building on ideas, so theft is encouraged. Don't be afraid of that. Try to stay focused, which can be hard, spending 15 minutes trying to generate 3 ideas per minute. That's a lot of ideas, but do try to do that. And then, as I mentioned, be visual, and use wild ideas. Don't be afraid to be like, yeah, wall of doom, but it's going to be made out of peanut butter. Like something that ridiculous, just pops in your head. Throw it out there because it may inspire someone to say, well, not peanut butter, but what about peanut shells? That would be a really low-cost way to make it, right? And all of a sudden, that's a slightly useful idea for this ridiculous wall of doom. Yeah. And then once you're done, you can sort the pile to divide to get them into themes, so you can sort of, just figure out what are your themes or what are your combinations, figure out do those themes actually make sense, and then often refine and combine the best. So those 2 ideas from each group don't necessarily have to be the ones you came up with, but ones that you think are some of the best of what you came up with. Do you guys have questions on that? I went over that kind of fast, so, but yeah. Okay, so then for the next hour and a half, you guys can take your 10-minute break and then come back and do the brainstorming, meet with me. And then please remember to fill out your muddy cards and include the hours per week on them, so that you think you're spending on the class, so that I just have a sense of how that's going.
But it's a sort of big blue box with a lid that you can open, and it has like a table built in that sits on.
Wait, so how big is it?
They make them in different sizes, but it's basically like this lid.
No, I'm doing a better drawing. I'm doing the same thing. It's a better drawing.
Go post it.
Wait, but it doesn't make sense. It's supposed to be a parabola, and it's
That's
like
supposed to make sense.
it looks like a funnel.
I like it. Steal your idea.
trying to make a parabola.
Well, then make it.
Wait, hold on. Let me explain what it is, though.
Oh yeah.
Oh, I'm trying to make a parabola. So it's a parabolic solar cooker.
That is not a parabola, let me just say.
That's why I scratched it out so I could grab a parabola. Just basically kind of stealing the idea from, I don't guess, our Soul Source. They do solar cookers and they're in the Himalayas and they're really mobile. You can fold them up and carry them around. So that was the idea.
That's a big drawing.
No, I'm trying to drop.
You're like, fine,
It looks
whatever.
like a funnel.
You can like redraw it and twist it over if you really want. Or you can just do it in wood.
My plan is to email out
Combination box and
template.
parabolic solar thing, heating, some kind of heating element that is.
So would that be like the liquid?
Yeah, that's a liquid. And shoot. So it'll have to cycle back. Oh, good.
Okay.
Yeah, that's what's happening.
It'll be like.
Yeah.
Cool.